we introduce EgoGen, a generative and scalable synthetic data generation approach, specifically tailored for egocentric perception tasks. Simulation and synthetic data generation have gained wide attention in various domains, including autonomous driving, human-robot interaction, and humanoid training. While they incorporate digital humans into their works, the synthesis of human motion in their works remains deterministic and unnatural. Moreover, they have a limited number of human agents, constraining their ability to integrate diverse body shapes, ethnicities, and realistic clothing into their simulations. For egocentric perception tasks, there exist several large-scale real-world data sets like Ego 4D, Epic Kitchen, and ADD. However, creating such data sets with rich and accurate ground truth annotations is expensive and raises privacy concerns. To address this issue, we propose EgoGen, a generative and scalable synthetic data generation approach to synthesize extensive labeled data for egocentric perception tasks. EgoGen consists of several core components. At the heart of EgoGen is a novel egocentric perception-driven motion synthesis model. Our key idea is to enable virtual humans to perceive their environment, thereby closing the loop on the interdependence between egocentric synthetic image data and human motion synthesis. To be more specific, given a scene mesh, the initial body pose and shape, and the target location represented as a green ball, we aim to synthesize natural human motions considering egocentric visual information as input. To avoid expensive depth rendering and stabilize the reinforcement learning training, we propose to use compact egocentric sensing as a depth proxy. The body pose and shape are simplified using body markers, and the body marker location and direction to the target are encoded with GRU. Egocentric sensing is encoded with GRU to capture temporal information. The distance to the target and remaining time are encoded using positional encoding. We use the PPO algorithm to optimize a stochastic policy. The actor and critic networks are parametrized by MLPs. Our model has several advantages. First, motion synthesis is driven by the virtual human's egocentric perception. Additionally, we can synthesize egocentric perception behaviors, such as looking in specific directions. Second, our model does not rely on a pre-computed global path. Instead, it lets virtual humans explore with their own egocentric perception. Third, our model can synthesize emergent multi-agent behaviors not seen during training without relying on multi-agent reinforcement learning algorithms. Given an arbitrarily synthesized motion sequence produced by our generative human motion model, we outfit virtual humans in diverse 3D textured clothing by performing automated clothing dynamics simulation with a state-of-the-art neural network. The embodied camera placement module supports simulating various head-mounted devices with different camera models and camera rigs. By positioning the camera on the head, we generate photorealistic egocentric synthetic data with rich and accurate ground truth annotations. EgoGen supports various cameras and camera rigs. We can render high-quality egocentric synthetic data with a rich set of ground truth annotations, including RGBD images, optical flow, surface normals, segmentation masks, object bounding boxes, world positions, and simulated motion blur. For egocentric perception tasks, we conduct several experiments to compare the motion quality of our model with baselines and perform various egocentric perception tasks to demonstrate the efficacy of EgoGen. First, we present qualitative results comparing our motion synthesis with baselines. We compare the generalizability and motion quality of our motion model with two recent works, Gamma and Demos, which synthesize human motions in static scenes through path planning. For a fair comparison, we improve their models with dynamic path planning. In contrast, our model does not require path planning at all. In the context of dynamic obstacles, obstacles move to block humans from reaching their goal. Despite augmenting previous works with dynamic path planning, they still encounter issues of penetration with dynamic box obstacles in the arm region. In contrast, we can synthesize collision-free motion sequences. Despite augmenting previous works with dynamic path planning, synthesizing realistic collision-free motion sequences for two people switching locations remain challenging. However, Our method demonstrates the ability to generalize, even though it is only trained in static scenes. In a more challenging scenario involving the synthesis of 4 people switching locations, previous works struggle. In contrast, our method demonstrates generalizability and higher motion quality. Here we further compare previous works with our model in a crowded setting. The task is to synthesize the motion of 8 humans switching locations, with each individual reaching the target located across the circle's center. Previous works failed completely. Even though our model is only trained on static scenes, we can generalize to more complex tasks not encountered during training and exhibit higher motion quality. We further qualitatively compare the motion diversity of our method with physics VAE. Physics VAE synthesizes completely symmetric crowd motion for stickmen only. The result is unrealistic when considering real human crowds. In contrast, our generative human motion model allows us to generate diverse crowd motions for diverse body shapes, incorporating variations in height and weight. This paves the way for diverse egocentric synthetic data generation. After comparing our motion model with previous works, we evaluate the effectiveness of our egocentric sensing. Using egocentric sensing as a depth proxy enhances the ability to see farther and explore more effectively. We substitute our egocentric sensing with a local map introduced in demos and adopt their encoding method. In a test scenario where the virtual human is in front of a long wall, relying solely on local information can trap the agent in local optima. In contrast, egocentric sensing enables the agent to walk across the long wall. We additionally present the ablation results of our 2-stage reinforcement learning training scheme. Given our high-dimensional and bounded Gaussian latent action space, direct RL training with hard penetration constraints can result in exploring unreasonable spaces, generating unrealistic human poses, as shown on the left. In contrast, our 2-stage RL training produces realistic human motions. In the last part, we present qualitative results of egocentric perception tasks benefiting from the synthetic data generated by EgoGen. These tasks include mapping and localization for AR, as well as human mesh recovery from egocentric views. Mapping and localization for AR aims to build a structure from motion map, using images captured by head-mounted devices as input, and to localize images with the map. Despite extensive data collection, mapping images in large open spaces remains sparse, as shown by the red cameras. The mapping and localization pipeline comprises several components. In the pair selection module, to cope with the domain gap and ensure valid matching between synthetic and real-world images, we enforce that synthetic mapping images match only with real mapping images, and real query images match with both synthetic and real mapping images. EgoGen enables virtual humans to explore large-scale scenes, generate dense egocentric views, and build more complete structure from motion maps. EgoGen shows potential for building mapping and localization data sets for AR and digital twin scenes and enhances privacy preservation. Egocentric human mesh recovery aims to recover human body pose and shape given an egocentric image as input captured by head-mounted devices. We use EgoGen to generate 105,000 synthetic depth data by simulating 2 virtual humans switching locations in ego body scenes. We sample gender, body shape, and initial body pose to diversify human motions. In addition, we generate 300,000 synthetic RGB images by randomly sampling body textures and 3D textured clothing meshes from existing assets and performing automated clothing simulation. We test the recent human mesh recovery model ProHMR with depth images as input on a real-world dataset, EgoBody test set. Here the mesh color denotes the vertex error between the predicted body and the ground truth. Compared with a model trained from scratch on EgoBody training set, the model pre-trained with our generated synthetic depth data achieves significantly improved performance. Furthermore, we extend the assessment to ProHMR with RGB images as input on the EgoBody test set. In contrast to the model trained from scratch on the EgoBody training set, the model pre-trained with our synthetic RGB data demonstrates improved performance. For future work, We intend to extend our current method to synthesize more detailed human motions driven by egocentric perception, such as sitting, lying, and hand-object interaction. This task poses a challenge, as, for example, when the agent sits on a chair, it must build a world model through egocentric perception and remember the chair's location when it is not in the field of view. We also plan to explore other egocentric tasks, such as egocentric point tracking and egocentric semantic segmentation. EgoGen may also enhance human-robot interaction by integrating our generative human motion model and lifelike human appearances into Habitat 3. The sim-to-real gap for egocentric robotic agents could be further narrowed. Thank you for watching.